All right, well, happy Friday. Today, our goal is to wrap up our discussion of the higher order differential equations. Like we saw last time, everything is virtually the same, just more. Well, same thing we're going to see when we talk about the variation of parameters, the one thing we haven't dealt with yet, but it's the same method. It's just bigger. It's just there's more to it. And then after we get done talking about that, I'm going to start you into systems of differential equations. Because just like other kinds of equations, we can have systems of them. Well, same thing with differential equations. So we'll start our discussion on that, which is the last topic for this class. So definitely at the home stretch. But before I get off and running here, do you guys have any questions on homework or that sort of stuff? Let me just mention exams. I'm in the process of grading. Some of you have gotten them completely graded. Most of you have not. They're coming. I'll have them for sure by Monday. So just get that out of the way. But any other questions from you guys, homework or otherwise? All right, I'm not hearing anything and I'm not seeing anything, which tells me we're good to go ahead and move on. All right, so let me go to a whiteboard here and we will go. All right, so last time we were looking at these higher order differential equations, right? And we saw that everything was the same, just more. And probably one of the more important things is that our fundamental set now is going to be a bit larger. And we're actually going to have the same number of functions in our fundamental set as the order of our differential equation. And so really all that did was just lead to the size of these things, but the process was still the same. This also means that for initial value problems, we're going to need let me just call it y naught, a y naught prime, a y naught double prime, all the way down to a y naught n minus 1. So we're always going to have the biggest one is going to be the derivative that's one less than the degree or the order of our differential equation, right? So it's really the same idea, just more. And so we saw finding the fundamental set meant factoring a polynomial or finding roots of a polynomial that was higher degree. Undetermined coefficients was, well, we make our guess, we just have to take more derivatives and so on and so forth. So luckily nothing there really changed much, just more. All right, well, let's talk a little bit about variation of parameters, because that was the one thing that we didn't get to last time. And we should probably see how that's different. So let's remind ourselves first about how this worked for second order. So do you guys even remember what I mean here when I say variation of parameters? What method that was?
All I think really is restrictions and Wronskian.
Okay, so this was the one where we put some restrictions on the derivative, which led to the Wronskian. So that's good. Anybody else remember any more about it?
Yeah, I guess system of equation is the same as Wronskian, I guess.
Okay, so we ended up with a system of equations, and we were using the Wronskian as the coefficient matrix. And then, do you remember what we were multiplying by, like what the whole point was?
It was to find an integrating factor, I think.
Okay, yep, it absolutely was. It was to look for integrating factors and kind of build. So basically what we did was we said if we knew we had y1 and y2 were our fundamental set, we were looking for solutions that were the form u1y1 plus u2y2. And through some restrictions and all that, we ended up with a matrix equation that looked like this. So u1 prime, u2 prime equals 0. And I think we called it g of t, where this was whatever our differential equation. So differential equation equals g of t. And so when Bradley said he remembers restrictions, the restrictions were what led to this equation. We just instituted the restriction y1 times u1 prime plus y2 times u2 prime equals 0 because A, we could. Because we had two unknowns, we could choose one of our, we can put in one condition that we want, right? So we did that because we could, and also because it made it so that the subsequent derivative was a little bit nicer. Things went away and led to that second equation, which was the y1 prime times u1 prime plus y2 prime times u2 prime equals g of t. All right, so this matrix, of course, is the Wronskian. Right, so that's our Wronskian matrix. And so what we saw is if we, let's call that guy, say W, then we got the U1 prime, U2 prime was equal to the inverse of that matrix, so W inverse, times 0 G of T. So that gave us U1 prime equals and U2 prime equals, which then just meant we could integrate to get our U1 and U2, which were our integrating factors, and we got our answer. So that's what it was like when we had second order. So now, of course, the question is, what happens if we extend this to higher order, right? What if we're talking about a fourth order differential equation or a 10th order differential equation or whatever? Okay, so here's how things are going to change. Now, our fundamental set, of course, is going to be y1, y2, y3, all the way down to yn. So it's going to be a little bit larger. But we're still looking for a solution that looks like a linear combination of those where the coefficients can be functions of t. So we're going to have u1, y1 plus u2, y2 all the way down to un, yn. And the goal is going to be to find u1 through un. Okay. But now we're going to be able to put on n-1 restrictions. Since we have n unknowns, there are really n-1 free choices. And so what we're going to do is similar to the last time, we're going to just start instituting some conditions. So for example, we're going to go with, sorry, hit the wrong button up here. We're going to want, say, u1 prime y1 plus u2 prime y2 plus all the way down to un prime yn. We're going to set that equal to 0. Why? Well, because we can. Because when we differentiate, like think about differentiating this thing. When you do that derivative, you're going to get from the product rule 2 pieces for each one of these, right? You're going to get a y1 prime times u1 and a y1 times u1 prime. All right, well, if we lump this up, then half of those things are gone, and we're left with only the things that have the y primes and only the u's. So we never actually get to a u double prime when we differentiate the next time. Okay, so then we differentiate again. that's going to give us some u1 primes times y1 primes and all that. And we're going to want to do the same thing where all of the things that now have u primes, there's also going to be attached to y primes after we take a second derivative. We're going to want that to equal 0 for the same reason. A, we can do it, and B, it's going to make all those things go away so that when we differentiate the next time, we don't get any double primes on the u. We don't care about higher order derivatives on the y's. Those are not a big deal. But it's the u's we don't want higher order derivatives.
That's
All right.
because we have to integrate it at the end, correct?
Yeah, exactly. And it's going to make it a little bit easier for us to create our matrix equation. If all these things are u primes, then that's going to be our vector over here. Right? So we continue this process until eventually the last restriction that we're going to put on for the 0, it's going to be u1 prime, y1, and I think we're going to be at n minus 2, no, n minus 1th derivative. 1 second, bar. Sorry, so it's going to be n minus 1 plus, and then all the way down here to un prime yn to the n minus 1 equals 0. But so these are our n minus 1 restrictions. No, I was right. It was n minus 2 because we started counting at 0. But then when we go to the differential equation, it's actually going to give us one more now at the very end. We're going to get u1 prime times y1 to the n minus 1 plus all the way down here un prime yn to the n minus 1. But that's going to equal the g of t. And so this last equation isn't a restriction that we're putting on. It's a result of going into the differential equation with all of these other restrictions. It forces this last guy. Now, notice that for each one of these, there's the u1 prime, and this next one has u2 primes, u3 primes, all the way to un prime. So we can kind of like pull those things out. And what it does is it gives us another matrix equation, just like this guy. But what it's going to look like now, clear this stuff. Because it's a little bit larger order, it's going to look like this now. So we're going to have y1, y2 down to yn times u1 prime, u2 prime, all the way down here to un prime. And then the next row, this is going to be y1 prime, y2 prime, all the way down to yn prime. And if we continue this all the way down, we're going to get to the n minus 1st. So we can get y1, n minus 1, y2, n minus 1, to yn, n minus 1. And this is going to equal zeros, a whole bunch of zeros. And then the last one's going to hold that g of t. So just like all the rest of this higher order stuff, it looks exactly the same. It's just larger. Now, instead of just the 2 by 2 matrix, we've got an n by n matrix. Our, I don't know, variable matrix here, let's just call it the variable matrix, now is going to have n entries instead of just 2 entries. And our answer matrix is going to have n entries where all of them are 0 except for the last one. So hopefully you notice that this guy right here is still the Wronskian. And so we end up with exactly what we saw last time, which is this thing that holds all the derivatives of the integrating factors is actually equal to the inverse of the Wronskian matrix times this other matrix that has zeros everywhere except the last entry, which is our G of t. All right, so the goal is actually exactly the same. We're going to build the Wronskian, then we're going to find its inverse, and then we're going to multiply it to this thing. That's going to give us our u primes. So after we have our u primes, we integrate them and multiply them to our y's. It's just finding that inverse now is going to be bigger, more. All right, there's going to be more stuff we have to do. All right, now what I want to do, let me go ahead and just start with an example here. And the reason we're going to kind of walk through an example is I'm going to show you a bit of a faster approach to this find the inverse. You probably remember that for the 2 by 2 for the second order case, finding the inverse was easy, right? I mean, we even have that fast way of finding the 2 by 2s of finding the determinant, right? Dividing by the determinant, and then, move things around, change some signs. And when you get higher, when you get bigger dimension matrices, like 3 by 3s, 4 by 4s, 5 by 5s, it's a little bit more challenging, but there is a faster way, and you probably saw it. Hopefully you saw it last quarter with Larry. If you didn't, I want to make sure that you see it now. All right. So anyway, let's just go with this example. We won't make it so that it's incredibly big or anything. We'll just go to a cubic, right? A third order differential equation. So let's say that we've got y triple prime plus y. No, let's make it plus y prime. This will make it a little more exciting. Equals, and let's use secant. All right, we'll go with a function that's not one where we could just easily make a guess, right? Because if this was just say sine, we wouldn't bother with variation of parameters. You could just go to undetermined coefficients. All right, so first things first, we got to build the Wronskian, which means we had to find a fundamental set. But I think you guys are used to doing that by now. Excuse me, where the very first thing we always do is find that solution of the homogeneous. So it is linear. It has constant coefficients, so we can just go to create the polynomial. This is r times r squared plus 1. So we have r equals 0 and r equals plus or minus I. So that means a fundamental set here is going to be 1 cosine of t and sine of t. I highly recommend that you use one. And I know that I think this came up, maybe it was last time, if not, it was 2 times ago. Remember when Bradley was like, wasn't that just C1? Yeah, like when we put it into the form, it'll be a C1. But you can choose any constant you want to be your fundamental set element, any non-zero constant. So just pick one. It's going to be a lot easier. All right, so there's that, which means now we can create our Wronskian matrix. So the Wronskian matrix is going to look like this. We're going to have 1 cosine of t and sine of t as my first row, right? That's my y1, y2, y3. You can do these in any order, by the way. It doesn't matter. I just chose to take them in the order that I wrote them. But if you wanted to do sine, 1 cosine, or whatever, feel free. It doesn't really matter. You will get a different inverse. However, once you do that multiplication down here, you will get the u prime things the values of the u primes, they'll just be in a different order, but they'll still be attached to the one that we are the y that we're going to multiply against. All right, so I'll do it this way. So then the next row is their derivatives. So we get 0 minus sine and cosine. And then the next row is going to be their second derivatives. So 0 minus cosine minus sine.
I have a question.
Yeah, go for it.
I'm just curious because, like, we got a matrix full of, functions and constants. And then I'm thinking about this in a linear algebra aspect. Are functions vectors themselves?
They can be.
Can be? Okay.
I mean, you can have a vector space whose elements are functions. Obviously, you have to have operations that are with them as well, right? Because remember, with a vector space, you always have to have an addition operation and a multiplication operation. So a function just by itself isn't necessarily a vector, but it is a vector in the vector space that's made up of all functions with standard addition and standard multiplication. So that's why I say they can be. I mean, in general, they are. Yeah. Just like polynomials are vectors, if you think about it the right way, right? Or matrices are vectors. So in a way, I've got a vector full of vectors. That's what a matrix really is anyway, right? Anyway. All right. So how are we doing so far? I mean, this is exactly the same process as we did last time. It's just now we got to find the inverse. All right. Well, technology will definitely do this for you. I'm pretty sure even like the TI-89, you can build the matrix using the functions and then do inverse and it'll give it to you. If the 89 can't, I know that there are lots of resources on the internet that can. But suppose we were going to do this like by hand. That's going to be kind of a challenge, right? So here's the deal. Let me give you a little tip. When it comes to y inverse, I know it's going to be a 3 by 3, but these guys right here, I'm putting the stars on, the first two columns, I don't care about. They are going to be completely useless and unnecessary when it comes to finding the U1 or the U1 prime, U2 prime, all the way down to UN prime. Do you see why?
Because of the zeros?
Yeah, that's exactly it. Because of those zeros. Because think about what we're going to do with this matrix. Once we get this matrix, we're going to multiply it by the vector 0, 0, secant. And so regardless of what's in those first two columns, when that multiplication happens, anything in that first column is going to get multiplied to this 0. Anything in that second column is going to get multiplied to the middle 0. I don't care about those. They don't impact anything. So really, the only thing that's going to matter is this last column. Okay, this is actually useful. Because imagine, I mean, this is just for a third order, right? But let's say this was, I mean, even just fourth order or fifth order. Instead of having to find the entirety of this matrix, I only have to find one column. Dude, that's awesome, right? That's going to be a huge time saver. So let's talk about how we can find that column. So I'm curious, because I wasn't there, but when you guys learned about inverses and making inverses, Did you guys learn about cofactor expansion?
Yes.
Yep. Okay, so where you can,
Yeah.
instead of looking at the entirety of the matrix, you can find the determinant of the minor, the one that you, after you eliminate row and column. And so you can use that determinant to help build your spot. Well, that's what we're going to do. All right, so let's think about first this spot right here. Right, so this is the 1, 3 spot because it's row 1 and column 3. And so to find the 1, 3 spot, we're actually going to do the cofactor expansion, or we're going to find the minor 3, 1. Okay, so what we're going to do is we're going to eliminate the third row and the first column. All right, so just for whatever your position is, just think I want to swap those two numbers for my rows and my columns. So I'm going to get rid of row 3, and I'm going to get rid of column 1.
Then it was multiplied by 1 to the, or negative 1 to the power of the column to the row.
Okay, yeah,
Something
and
like
then
that.
there is going to be that, there's going to be a either plus or minus. And you're right, it's a negative 1 to the sum of the rows and columns. And then the other thing we have to do is we have to divide by the determinant of the original matrix. So there are still a few things that we have to do, but let's start with finding this determinant. Well, this is now just a 2 by 2, so we're going to get cosine squared minus negative sine squared.
I see what you did there.
All right, which is 1. Okay, now we also need the determinant of W. So if we go back to the original determinant of the original matrix, we're going to get 1 times minus sign times minus sign, so that's sine squared. We're going to get cosine times 0, that's nothing. Sine times 0 times, okay, that's nothing. Sine times minus sine times nothing. Cosine 0 minus, okay, nothing. And then 1 times cosine is a negative cosine squared. So again, we're subtracting a negative cosine squared. And oh, hey, look, that guy is 1 as well. So for this entry, we're going to get, so we'll call this W inverse 1, 3. It's going to be negative 1 to the 1 plus 3 times 1 divided by 1. And those two ones are different ones. The one on top came from the determinant of the minor, and the one on the bottom came from the determinant of the matrix itself. All right, well, negative 1 to the 4th is 1 times 1 divided by 1 is 1. So let me go ahead and just erase this little box and stuff, and we'll put in what we know that number is. So this guy is 1. Now, I know that that feels like we just did a lot of work. It doesn't actually usually take that long. Obviously, we're kind of explaining what we do. For the next ones, it'll go a little bit faster. All right, so let's go to the 2, 3 spot. Now, for the 2, 3 spot, we have to look at a different minor. So let me erase that 0. Put that back in. Okay, so now if we're in the 2, 3 spot, we have to do the minor after we eliminate row 3 and column 2. So we're going to take row 3, and we're going to take column 2, we're going to eliminate that. So let's find the determinant of what remains here. Well, that little 2 by 2 is going to give us cosine minus 0. So it can be the inverse in the 2, 3 spot. Well, let's start with, we're going to have minus 1 to the 2 plus 3 times, now we've got cosine, and then we need to divide by the determinant of the original matrix, which was 1. So we do all of that, we're going to get negative cosine of t. So hopefully you see that's a little bit faster. All right, so let's go get this last spot. So this last spot is the 3, 3 position, which of course means we need to eliminate the 3, 3 position, right? Because you swap them. So we're going to eliminate row 3 and column 3, and we're going to look at the determinant in here. So let's go ahead and do W inverse 3, 3. So we're going to get minus 1 to the 3 plus 3 times, all right, well, this determinant, we have minus sign minus 0, so minus sign of t, and then again, we divide by the Wronskian or determinant of the whole matrix. And that leaves us then with a minus sign. So there's the only part of this matrix that we care about. Well, we got it. Now we're going to be able to multiply that to the 0, 0 secant so that we can find out what the u1 prime, u2 prime, and so on are. So we can find u1 through un, multiply those to our y1 through yn to get our solution, our particular solution. Okay, so before we move on to that next step, questions on this building of this column? We good?
I just want to be clear that that will always be the case where the first 2 columns won't matter, or well, depending on the size.
Yeah, it's going to be the all but the last column.
Got it.
So if we've got a 10 by 10 matrix, the first 9 columns are irrelevant. It's only the last one because of the fact that there are going to be zeros in every entry of this matrix that we're multiplying by, except for the bottom function. Here's another little trick for the plus minus stuff. If you're like, man, I'm not going to remember, take -1 and raise it to the right power. Another pattern with this for the plus minus is if you go to these positions, starting with a plus here, just alternate every time you take a step one way or the other. So obviously the first ones don't matter, but if you just start in the upper left corner with a plus, you can go across the top, plus, minus, plus, and then go down that back column. So that was a plus, this is minus, this is plus. So that's just another little way that you can remember that without having to deal with a formula. Okay, so we're almost there. Almost there. I mean, there's still quite a few steps here, but we've done, I think, mostly the bulk of the work by finding that inverse. Right? So let's take that inverse and multiply it by the 0, 0 secant. So obviously we're going to get 1 times secant. So we get u1 prime is equal to secant. We're then going to get minus cosine times secant. So u2 prime is equal to negative cosine times secant. And then u3 prime is going to be minus sine times secant. Well, let's simplify these a little bit. Cosine times secant is 1, so that's just -1. Sine times secant, that's tangent, so we get negative tangent. So there are our u primes, which then means we need to go ahead and get our u's. So we're going to get the u's by integrating these things. All right, well, u2 is easy. Oh, it's just negative t. I don't know if anybody remembers the integral of secant. Most people don't.
I want to say it's 1 over 1 minus x squared, or t squared.
That is not it. It's actually got a natural log. It's the natural log of secant plus tangent. That was one of those weird ones where there was a miracle step. The multiply top and bottom by secant plus tangent, and it just magically works out. Anyway, you saw that one literally forever ago. That would have been back in like January of 2020 or something like that when you learned that integral. One of those many times, like Bradley was saying, with the multiply by 1. Yeah, that's just the right form. Anyway, so that's the u1. So u2, of course, is minus t, and then u3, integrating tangent. Again, I don't know if anybody remembers how to do that, but that's one where you make it sine over cosine, and then notice that the top is the derivative at the bottom and all that. You get the natural log of cosine of t. All right, think about the differentiating logs. You put what's inside on the bottom.
It's chain rule, right?
Yeah. Anyway, that's not important. I know you guys can get those integrals somehow. All right, so there are our u1, u2, u3. So remember what those were. Those were the integrating factors for our y1, y2, y3 that we're using to build our particular solution. So we know then that y particular is going to equal 1 times natural log of secant plus tangent plus cosine of t times negative t. Make a little more space here. Plus sine of t times the natural log of cosine. Right, so you just take these in order and multiply them in order to the way that you set them into the matrix. So remember at the beginning when I said you can, do them in any order. It doesn't really matter. If we had ordered this in a different way, we would have gotten a different inverse, obviously, because we had a different matrix. But when we multiplied that by secant, we would have actually gotten these same 3 things, just in a different order that would have corresponded to the order that these 3 original functions were put in, so that this particular solution would have ended up being the same. So you can't lose, you can't go wrong with how you decide to order them. All right, so there's our particular, which means now we can actually write the solution to this. So we're going to get C1 times 1 plus C2 times cosine plus C3 times sine. So that was our homogeneous piece. And then we add to that our particular solution. So we're going to add then natural log of secant plus tangent minus t cosine plus sine times the natural log of cosine. And that right there, sorry about the extra slash. This is the solution to our original differential equation.
Gross.
Yeah, but think like a mathematician.
We can
So
do it.
Yep, mathematician's like, boom, there's the answer. I got you an answer. Someone else goes, it's gross. And you're like, yeah, but there's the answer, right? So anyway, so just notice that the process is identical. It's exactly the same as what we did before. There's just more. And that's kind of the moral of the story with these higher order things, is that you have a higher order. Okay, you got a higher order, whatever. I'm still going to do the same things. I'm still going to find my solution homogeneous. I'm still going to find a particular solution. And to find that particular solution, I'm either going to, make a guess, or if I know some things, I'm going to create some integrating factors and blah, blah, right? Like, honestly, you guys know I'm not a huge fan of diffie-qs, right? I think I've made that pretty clear. And this is kind of why. It's boring. You do the same thing every time. It's just like, all right, what are you going to do? Well, I'm not sure. So I'll multiply by an integrating factor. And I mean, it's impressive that it works, right? I mean, don't get me wrong. It's definitely impressive that it works. But it's like, God, how many times am I going to have to multiply by a u and find out what that random u is through some, method like this? And then it's like, yeah, and this method is no different than the method before. Like, in fact, this is the exact same method that we did like week 1 or 2. You remember the first time we saw integrating factors? I mean, at this point, I wouldn't be surprised if you're like, no, I don't remember, because it was way back in April, and it was for the linear first orders, and we kind of went through this whole convoluted process. That was where we had to get the negative p and then do e to the integral of the negative p, and you remember all that? that
Yes.
that is exactly what we just did right here. That's just the case, though, for a 1-by-1 matrix, right? I mean, think about it. If you've got a 1-by-1 matrix. Let me just do this here real quick. Before I erase this, we all good? Any questions on?
I have a question, but it can
Okay.
wait till after what you're about to show us.
Even if I erase, though, we're okay?
Yeah, you're cool. Yeah.
Okay. All right, because let's just think about this. Go back to a really simple linear first order deal that we did back in the day, right? So you have something like y prime plus, let's do constant coefficient just to make life easy for us. So let's go plus 2y, and then we'll make it equal 2y. And just to make life easy, let's say it's e to the t. Okay, so I know we had a different way of solving this before, but now let's think about it in terms of how we've been solving all these higher orders. So the very first thing you're going to do is you're going to create your polynomial. R plus 2 equals 0. Okay, so R equals -2. So that means that my y1 is e to the -2t. Okay. So in terms of like the Wronskian business, all right, well, so then here's my Wronskian W. It's going to be a 1-by-1 matrix, which is just e to the -2, e to the -2t. So I need an inverse to the Wronskian. Well, if it's a 1-by-1, the inverse is 1 over that. That becomes e to the 2t. All right, so then my matrix that I'm multiplying it against, there are no rows of zeros. It's just the e to the t. So I'm going to get u prime, we'll call it u1 prime, is equal to e to the 2t times e to the t, which is e to the 3t. All right, make some more space over here. So then that means my u1 is going to be 1/3 e to the 3t, because I got to integrate this, which then means my particular solution is going to be that 1/3 e to the 3t times e to the minus 2t, right? That's u1 times y1, which is 1/3 e to the t. So we'll put that all together, and we get that our solution is c1 e to the minus 2t on that guy, plus 1/3 e to the t. And there's our answer. Now, if you go back, and look at what we did with integrating factors way back in chapter 1 or wherever it was, you're going to see a completely different method, right? It's going to, I mean, we still found the u, we did the e to the minus integral of p, and right, and then you found that thing, but then we had to divide by that and then multiply by the integral of the other side, blah, 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 right? It's going to bring you exactly here. So these methods that we've learned, the undetermined coefficients, the variation of parameters, they actually apply even back to first order differential equations. We just I didn't tell you about that at the time, because can you imagine if I had started with this kind of theory, this kind of process? You guys all would have been like, what the hell is this class going to be like? But we eventually got ourselves here, and now we can look back and go, oh, we actually were doing that. So that's beautiful, but at the same time, that leads to me saying, yeah, it's boring. What do? Well, every time I create the Wronskian, and I find the inverse, and then I multiply it. No, okay. It's really procedural, but that's not the kind of thing that I like. I know many of you probably love that, where it's like, here are the steps, here is the recipe, every time do it this way. And that's awesome. If you're one of those people, more power to you. For me, mind numbing, which is why I like things like linear algebra, or I like things like trig, specifically identities, because think about that. That's not a follow the recipe. That stuff's a how do we go from point A to point B following the rules. So I'm the type of guy who I love doing proofs. I loved that. But that's also why I ended up being a math major, because I liked doing that stuff. And that's what you do when you're a math major, right? So anyway, enough about me. But hopefully you're kind of seeing that, yeah, it's exactly the same process. The exact same process can be done even for the things that we did way back when. All right, Bradley, you said you had a question. So why don't you go ahead and throw that at me?
Yeah, so on which I don't know if you would expect this on an exam, but if we were given a problem such as the one we just did,
yeah,
would you want us to go through the differentiating in algebra of setting the parameters like or conditions, or could we just go straight to the Wronskian and just go?
Oh, and now?
Yeah.
Just go to the Wronskian. I don't care.
Cool.
Yeah, and I mean, you guys know that about me anyway. It's like, as long as you're doing a valid method, I don't care, unless I specifically were to ask you, right? Like if I said, I want you to do this one using undetermined coefficients. Okay, well then do it with undetermined coefficients. But nah, I mean, we give you the tools so that you've got them at your disposal, and you can reach in and be like, oh, I'm going to use duct tape for this one. I'm going to use pliers for this one, right? Well, that's basically what this is. You can look at your problem and go, what's going to be the best way for me to get there? And depending upon who you are, like this one problem now, we've got tons of ways we can get there. I just showed you the variation of parameters way. There's also the undetermined coefficients way, right? Where again, we start with the e to the minus 2t, but then we go, Well, let's make a guess on the form. This thing is exponential, so I'm going to guess that my particular is of the form a e to the t. Okay, well, let's just see what happens. Y prime is a e to the t. I plug that in. I get a e to the t plus 2a e to the t equals e to the t. Divide out all the e to the t's. I get 3a equals 1 and a equals 1/3. Okay, cool. So my particular is 1/3 e to the t. Hey, look, it was 1/3 e to the t, right? So you can do it that way. You can't do reduction on order of this because it's just the one variable, or the one derivative is just first order, because reducing the order is basically getting your answer. But yeah, now there's lots of different ways. I mean, shit, do this with power series. Do it with Laplace transforms. They're all going to lead you to the same place. So just think about now the power that you have because you've learned all these different methods. You have a lot at your disposal to handle differential equations. So in the future, whenever you run into them, and where that's going to be, I can't tell you, right, without knowing exactly what your field is. But there's a really good chance that you're going to run into differential equations somewhere, knowing what I know about where you guys are going. And now you've got those tools. And it might be when you get there, you're going to have to stop and go, wait a minute, I remember doing something like that. You have to look into it a bit. But it should come pretty fast because we've now seen it. All right. Anyway, so good for that one ish, maybe, kind of, sort of. All right. Anyway, so I don't think I need to show you another example of variation of parameters because they're long, they're boring, the answers are ugly, but it's always the same. Create your Wronskian, find the last column of the inverse. I mean, find the whole inverse if you want, but all you need is that last column. I suggest using the cofactor expansion idea, the minors, to build that column. Then multiply that column by whatever the non-homogeneous piece is. Integrate each of those to get your u's, multiply those by the original y's, and there's your particular solution, right? So it's very, very procedural, nice and simple recipe the whole time.
Those derivatives can have functions multiplied to them still, right? Like other t's? Or would we have to go about it differently?
What do you mean by those functions? You mean the like what it's equal to at the end, or
No, like for our example, we did y triple prime plus y prime. Can they have other functions multiplied to them?
Oh, yes, absolutely. What that's going to change, well, okay, so you always need to make sure that your highest order derivative is just by itself, right? So like if you had, say, t times y triple prime, make sure you divide that t out to everything. So you just have the y triple prime by itself. But then, yeah, what that's going to change is it's going to change your fundamental set, or how we find the fundamental set of solutions. So like think about this one, when we just went to r cubed plus r equals 0 to find the one cosine and the sine. That was because they had constant coefficients. If they don't have constant coefficients, then we have to use one of our other methods, like, for example, the Euler equations. Remember, those are the ones that are the t squared times y double prime plus something times t times y prime, right? That one, we find our fundamental set in a different way. But once you have that fundamental set, then you make the Wronskian, then you find the last column of its inverse, then you multiply by whatever's over here, right? And so, yeah, if there's other stuff in there, it just changes how you find your fundamental set, how you find the solution to the homogeneous. But once you have the solutions to the homogeneous, now it's cruise control. All right, any other questions on that? No? All right, so there you go. There's higher order derivative or higher order differential equations. Nothing new, just more. And there is sort of that. There's any of these one process works for all orders, even the first orders that we saw way back when. All right. So actually, I think we're going to stop here. This is a good place to stop. We'll save the systems of differential equations for next time. So on Monday, we're going to dive into that. We'll talk a little bit about why we would care about systems of differential equations. And I'm just going to tell you, in my experience, those are very common. And we'll talk about the process that we use to solve them. And I'm just going to give you a little bit of a tip, something that I think you should look over just to remind yourself about before Monday, because this will help you. Go back to your linear algebra stuff and review a bit about eigenvectors and eigenvalues, because we're going to make use of those. Get excited. You're going to see a reason why we care about eigenvalues and eigenvectors. All right. So we'll do that on Monday. Other than that, I think the only thing we need to know is we've got just this one more chapter to go. There are homeworks that are due Monday night, but I don't believe, I think they're only the higher order stuff. So you should be good with that. But yeah, we got 1 week to go. Get excited. We're almost there. All right. So everyone, I hope you guys have an awesome weekend, and I will see everybody on Monday.